So this lecture is largely a meditation on the informal principle that we might state as isomorphic structures or objects. I don't think that makes any essential difference here. If a structure is thought of as finitely many objects, and we have the habit of putting finitely many things together into one thing in mathematics. I've already commented on the second word. The first, isomorphic, needs no explanation to my mind because we are all mathematicians, and that's where the meaning comes from. But the last word, on the other hand, is much more delicate. Same. What does it mean? Well, identical, you might say, correctly, but then you've just changed the word from same to identical, and they have the same meaning. So I find that it's called for to say something about the possible interpretations of same, and especially what is the relevant interpretation for this talk. And to do that, let's go back to Frege's canonical example of 2 plus 2, 2 times 2, and 2 to the power 2. So what he noted was that these expressions are, of course, different, syntactically different. Moreover, although they have two equal parts, all of them, they have different sense, as in Frege's terminology. And that's also clear. Addition and multiplication doesn't mean the same thing. So what is it, in what way are they now the same? Well, the standard mathematical way of trying to say that is that, well, the expressions and the meanings are different, but the objects are the same. And Frege expressed this by means of his distinction between expression, sense, and reference. Ausdruck ist in Bedeutung. And as I've already said, the expressions and the senses are different. So it's natural now that this talk about saying that the objects are the same amounts to nothing else but saying that these meaningful expressions are co-referential, have the same reference. Now, in one way which he liked of expressing this is to say that we have one and the same object, namely 4, but it's presented or expressed in 3 different ways. Verschiedene Gegebenheitsweisen. So Gegebenheitsweise was one of his ways of explaining the notion of sense, Sinn. Now, if we look at this in type theory now, it's clear how you would write it. So the natural, the first way in which these are the same is definitionally the same, or definitionally identical. And I'm trying to stick here now to the word same or identical, and thereby staying with the practice of reserving equal for equal in some respect. So, I mean, 2 people may be equal in length or equal in weight or equal in eye color or something like that. That's the traditional way of using equal as distinct from identical. And that fits us very well in mathematics because we have masses of ways in which we want to consider things to be equal, but if we say that some two objects really are the same, then there isn't so much choice left any longer. This is no doubt the natural way of the first way of formalizing a type theoretically, and that fits with the with identifying co-referentiality with definitional equality. So definitional identity perhaps is the same as co-referentiality. And then we also see how the Frege's distinction between sense and reference comes out type theoretically, namely co-referentiality just means that these expressions, when we evaluate them or compute them, we get the same value, namely 4 for the successor 4 times operating on 0. So the sense-reference distinction comes out in a very clear way in type theory. Now let's go to the very beginning. In a presentation of type theory, where do you have to begin? Well, always by displaying the forms, the 4 basic forms of judgment. So I will do it in this way. Now here we have immediately the terminological problem that we have spoken a lot about. So then let me propose the following, that Vladimir, in one of his lectures, I think more or less subconsciously, wrote in some places type and in other places type. So here we have a possible distinction to make in writing. It's not good for talking, unfortunately. But I have used this terminology instead so much that I feel inclined not to change it in this lecture. So that means that if you prefer this, just replace set by type with small t everywhere. And then apparently there is trouble here also, because type with capital T in Koch means type with small t, but that's not my fault. Anyway, the 4 basic forms of judgment, as we know, are the following. And here, for simplicity, I'm not bringing in the logical framework, except in some places further on where it's kind of unavoidable. But to make it as simple as possible, I'm doing everything on the set level. So A is an element of the set A in such a context, and 2 elements of A are equal in the same context. So this is how we normally write it. Now, if we apply an ordinary school grammatical analysis to these forms of judgment, the first thing is to see what is the subject and what is the predicate. And that gives the following result. Well, this says that A is a set depending on these variables. So clearly, here is the subject, and here is the copula and the predicate. That means that, and similarly in the second form, A and B are identical sets depending on these variables, means that A and B form the subject, and R is the copula and then the predicate. And similarly here, A is an element of A, all of this is the predicate, and here you have a combined subject. So that means that we can write these four forms more compactly by saying that they are instances of the following. A is an object of category C, and A and B are equal objects of category C. So now we have a terminological problem here, again, as usual, because MacLean simply stole the term category from Aristotle, thinking that nobody had any use for it any longer. And he stole functor from Carnap, also thinking that the communities were sufficiently disjoint. But in the case of category, I think it doesn't cause too much problem, because in philosophy or philosophical logic, it's normally the Aristotelian sense that is meant, and in mathematics it's MacLean's sense. So here, for instance, I suppose it's immediately clear that I mean the philosophical sense of the term category. So these two are instances of this form, and these two are instances of this form, provided we let C be either set in this context or element of A in this context. So these are my categories. And then you see the connection between the concept of category and form of judgment, namely that a category is simply the same, or better, is the same as a form of judgment, or better, two coupled forms of judgment. So these two coupled forms of judgment correspond to this category, and the two last one to this category. Now, why am I saying this? Well, it's because of the notion of identity. Because if you ask what is a category, I mean, what does the word category mean? I think the appropriate answer is that a category is defined by laying down two things. First, what an object of the category is, and secondly, what it means for two objects of the category to be the same or identical. Well, that means that there is no uniform meaning of identity, because for each category you have to explain what it means for two objects of that category to be identical. In this case, explaining what it means for two dependent sets, respectively two dependent elements, to be identical. And this, these two parts of the definition of a category are usually referred to by saying that first you have to give the criterion of application for the category in question, and secondly you have to give the criterion of identity. And it's that criterion of identity which defines what it means for two objects of the category in question to be identical. Now let's ask ourselves, what are the formal laws that govern the relation of definitional identity that I'm considering here? And that's something we all know very well. So the first law, no doubt, to write up is that what is to be defined should be equal to the defining expression or object, if you prefer. So here there is also a problem. I mean, it was the defined thing and the defining thing, definitum and definiens, but there it's Russell. I don't know why he changed definitum into definiendum, but I stick to the more usual formulation. So that's the first law, and then it is the principle that we may substitute equals for equals, and I will just call that substitutivity. And then, of course, reflexivity, symmetry, and transitivity. And finally, these two rules whose crucial character in type theory can hardly be overly stressed, namely that if A is an object of type A and A and B are definitionally equal. And now I'm omitting contexts in the using a natural deduction style, that is always supposing that there may be assumptions that things depend on above. Then A is of type B and the corresponding rule. So now, after these preliminary explanations of the notion, yeah? No, I don't treat it as such. I spell it out differently. By substitutivity, I just mean that if you have a complex expression for, not a whole judgment, but something expressing an object, then we may replace any part of that object by a part which is definitionally equal to it, and definitional equality is preserved. So after these preliminary explanations, it should be clear that isomorphic objects, if isomorphism is defined in the usual way in mathematics, they are not the same, not definitionally identically. So that's an answer to the original a way of responding to the original sentence. But that's not the end of it, because the question arises, of course, immediately, can we nevertheless treat them as such, treat isomorphic objects as if they were identical? What does that mean? Well, it means to my mind clearly that can we treat them as such, that is to say, follow the same laws that we use for definitional identity, although they in reality are not identical. Well, what's the answer to that question? Well, in the first case, definiendum equals definiens, there is no problem. Substitutivity is what this lecture is going to be about, basically. Reflexivity, symmetry, and transitivity, I think I will not have time to say much about. I hope to have time to say something about reflexivity. And then we come to the two crucial laws here. And there, it seems to me that the answer is just clearly no. It's unthinkable that we could replace that identity sign by an isomorphism sign, and similarly here, because if we have that A is of type A and we have some kind of notion of isomorphism between sets or types, then we cannot conclude this. There will always be a coercion that has to come in so that we only get phi of A is in B. And similarly, of course, in the other case. So these are the laws. It's laws of this kind that we should expect if we start going that way to introduce isomorphism there. And as I said, of course, So that is a very negative start for this lecture, but there is a positive result, namely that I want to justify the following claim. I'm a bit hesitant to call it theorem. I mean, if you internalize this, then I would certainly call it a theorem, but in the way I present it here, I'm a bit hesitant to call it theorem, rather just take it for how it's stated, that every definable object of constructive type theory is invariant under isomorphism. So here the term invariant under isomorphism here could be replaced by simply is extensional. Wouldn't make any. So extensional with respect to the various isomorphisms that you have between objects of different kind. Now this means that, as you have seen already from the title of my talk, that suddenly, and it's a surprise for me, we are on Tarskian ground. I mean, that could have been a title of a paper of Tarski's, and since I couldn't find one with the title, I thought I could use it for my talk instead. And because Tarski was the first to ask himself this question and provide the positive answer in the case of the simple theory of types. In this paper, since he was so meticulous about references, this refers to the year for which this fascicule is, of which this is the result. So the paper is only printed in 36, so it's listed under 36 in the collected works. Now there he established precisely this, but for the simple theory of types and for the standard notion of isomorphism between individuals that you have at the bottom of the simple type hierarchy. And this is nothing but the same kind of theorem for dependent type theory. But there is a big difference, namely that I will make the notion of isomorphic or isomorphism between sets as weak as is at all possible. And nevertheless, it turns out that this is a very rich and interesting structure. So now let's go back to the forms of judgment, which have disappeared probably. Oh, here they are, yeah. So let's start with the first one. And now I will write out variable dependencies in the usual old-fashioned way, because although it involves a lot of writing, I think it's necessary for what I'm doing. Well, what I mean is rather, of course, eventually one will have to write this compactly so that it can be put on a computer, but the problem is with that compact writing, it's difficult to take in better to begin this way. Now, let's suppose that we have a notion of invariance written this way for any category of objects or kind of objects in type theory. Then what should we expect in this case, for instance? Well, we know it's part of the definition of this that capital A preserves definitional identity. But now what happens if we replace definitional identity by isomorphism instead? Well, naturally we should expect that A1 of x1 up to xn should be isomorphic to A of x1 prime up to xn prime, provided x1 and x1 prime are in A1 and x1 is isomorphic to x1 prime, etc. xn is in an of x1 up to xn minus 1 and xn prime is in an. And moreover, xn is isomorphic to xn prime. Here. Thanks. So this is the no, it will be typed, but I start from having it untyped here because so now deciphering this in turn constructively, what should it mean? Well, it should mean that we have an isomorphism P, let's call it, between these two sets. And what will that isomorphism depend on? Well, it will depend on x1 and x1 prime. And here we must expect to have a proof witnessing the isomorphism of these two, and similarly all the way up here. So let P1 be that proof. Then this relation which relates these two will have to depend on, and this I will now take to be the weakest possible form of isomorphism I can think of, namely just a relation between these two sets, which tells you which element in one set corresponds to which element in the other set. And here now we have to put x1 prime in A1 and P1 proving that x1 is isomorphic to x1 prime, etc. xn in an. And now the important thing is Pn proving that xn is isomorphic to xn prime. Yeah.
Just to clarify that I understood your answer to me correctly. xn and xn prime are different types, but maybe we state that they're isomorphic, we try to think of the notion of isomorphism.
No, it's untyped in the sense that I do not write things out yet, but isomorphism will be, I think Thierry has used the term heterogeneous equality or identity, and that it will be throughout. This was for the first form of judgment. Now the second and fourth form, there the answer is simple, because the justification of my claim that I'm in the process of giving will contain as part of it that this whole construction that I'm making is a model construction. And it's part of the definition of model of type theory that definitional equality is interpreted definitionally. So that means that we have no choice in the second and fourth line here but to take the interpretation to be definitional equality. But in the case of the third line, we must, of course, do the analogous thing here, namely, namely we must have a proof, little p, of these arguments, x1 prime p1, xn prime pn, a proof that little a of x1, it's the little a there, little a of x1 up to xn, and little a of x1 prime up to xn prime stand in this relation to each other. So we should have a proof of capital P of x1 prime p1 xn prime pn. That's a relation between these two sets, and hence I can apply it to a of x1 up to xn and a of x1 prime to xn prime. And the context is the same. It's a context that I well could call gamma star, for instance. So this means, yeah. Exactly. We have one specific one which we construct by recursion over the build-up of the expression for the type.
This depends on the previous one.
Yeah.
Like the notation of is equal actually leaves out the fact that it depends on the
Yeah. Exactly. So now for n equals 0, the simplest case, what does this amount to? Well, it amounts to saying that if we have a set, A is a set simply, then we will have an isomorphism, which I've called P here, between A and itself. So I will have a P which relates A and A. And we should interpret this as the formal expression of the idea that capital A is invariant under isomorphism. So by definition, a closed set, fixed set, is invariant under isomorphism, provided we have equipped it with an invariance relation P. And similarly, for the third line, and n equals 0, little a here is invariant, provided we have an invariance proof, little p, that's what this reduces to when n is equal to 0, which proves capital P, that capital P applies to that element and itself. So this says that little p is invariant. And it doesn't make sense to speak of the invariance of an element unless the set to which it belongs is invariant, because we need this P here in order to say that little a is invariant. Now, so what I just said is that invariant for closed things is the same as self-isomorphic. Yeah, with this treatment, I mean, now I've explained how the four forms of judgment are interpreted in this model. And it remains basically to go through all of type theory and see how it comes out. And the systematicity of the rules is, of course, extremely essential when it comes to matters such as this one. There are not so many full-scale models that we have of type theory so far. The old model of convertible terms that came from Tate's proof, and we have realizability interpretations, and we have the subset model that Michael spoke about yesterday. Yeah.
If we have a constant, we are free to supply with any relation?
Yes, yes, exactly. I mean, if we have a basic constant like capital N for the natural numbers, I simply can define myself that relation. So now this is a model construction, and it's always elaborate to. It's somewhat like the early days of set theory, when the first non-standard model was the constructible sets, I believe, or almost the first. And we shall see that this is related to that, actually. So in a model, we have to associate with each well-formed expression of the theory or the language its interpretation in the model. And in this case, like in the other models that I mentioned from the 70s, this interpretation will be a pair consisting of two things. Namely, one thing which I will call a dagger, and another thing which I will call a star. Now, a dagger is simple, because a dagger is just the interpretation of A in the standard model, that is the intended interpretation of A. So this is the intended interpretation. So what is the intended interpretation? Well, it's the interpretation which is defined, as we know, by saying that the set expression n, for instance, is interpreted as the set n, the numerical expression 0 is interpreted as the natural number 0, the interpretation of a numerical expression of successor form is just the successor of the interpretation of A, etc., for all operations. Now it's this which I will take advantage of by allowing myself something which is in general dangerous, namely to omit this here to make things look more workable. But we must remember one thing at least about the dagger, namely that I cannot define the intended interpretation by saying that a dagger is going to be A for any well-formed expression A. That's not how we define a model. We always do it by recursion on the build-up of the expression whose interpretation we are defining. So what about this law? Well, it holds, of course, in the sense that for each specific expression in the theory, by grinding out this algorithm here, we will establish this. But it doesn't hold schematically. And so that is exactly the same situation as with Tarski's material adequacy condition in the Wahrheitsbegriff paper, that for each instance something holds, but it doesn't hold schematically. So enough now about the dagger. Then the star is the crucial thing, and A star will simply be the proof that a dagger is invariant. Right. So now you have the explanation why I have referred here to Dan's and Bob Harper's paper on two-dimensional type theory and to Thierry's talk on the setoid model a couple of weeks ago, namely that this consists of two things, and hence it's natural to say that this interpretation is two-dimensional in precisely the sense of Dan and Bob Harper. So now we have to go through the rules, and of course it's out of question to go through all rules, but take a sufficient number so that the very systematic pattern of this becomes visible. So let's start with the context and the introduction of variables. So I think we have already seen that if we have a context gamma of this form, A1 up to xn of A, it's clear that I have always taken its interpretation to be a context which is 3 times as long, where I introduce a companion to x1, which I call x1 prime, and a proof that they stand in the relation A1 star to each other. And then when we come to the last clause, it will be xn as before, and its companion xn prime, which has the different type now, an of x1 prime to xn minus 1 prime, and finally the proof pn that they stand in the invariance relation to each other. And that invariance relation, you see that's already something, an star, depending on 3 times n minus 1 previous variables, x1, x1 prime, p1, etc., xn minus 1, xn minus 1 prime, pn minus 1. And what is an star with those arguments? Well, it is a relation, because of what I have already said. It's a relation between an of x1 up to xn and an of x1 prime up to xn minus 1 prime. And that means that I can well apply it to xn and xn prime. So this is how contexts are interpreted. And then if we go to the rule of variable introduction, so we have gamma. Gamma is a context, and A is a set context gamma. If we take this rule, which gives you the variables as terms, then it's clear how we have to interpret the variable now. We have to define the star of this. And what should it be? Well, x star should be something here, which is typed by what? Well, that should be clear from what I've already said. It should be A star, but now of course A depends on all these variables, so it's A star of all these variables, 3n variables, those, these, and also xn, xn prime, and pn, 3n variables here, applied to x and x prime. And that's precisely now, I should say, the interpretation of gamma comma x in A star will be gamma star followed by x in A, and now I'm not writing out the arguments, x prime in A with the changed arguments, and P finally, which belongs to precisely this, is typed by precisely this. So that means that I can interpret x star as P. So now let's go over to at least one ground type, and I had meant to take the natural numbers naturally, but to save time, I'm taking an even simpler case, namely a bool. And already in that very simple case, the pattern will be visible. And then I hope to say something about the more delicate cases, namely pi and the universes. So we know the introduction, formation, introduction, and elimination and equality rules for bool. I need not write them up. And now I have to define bool star, the interpretation of. And since I'm putting a star on all the standard constants, that means that I get twice as many rules as in the original theory. So we'll have a bool star formation rule to begin with. And what will that say? Well, it will say that if A and A prime are in bool, then bool star of A and A prime is a set. Natural to think of it as a binary relation, as a propositional function, of course. Or with what is equivalent to this rule is, of course, to just write that bool star is a binary relation on bool. So that's the formation rule, and then we have the introduction rule for bool star. Which is the obvious one. I want to say that 0 and 1 are related to themselves, so I need to introduce a proof 0 star, canonical proof 0 star, that 0 stands in the relation bool star to itself, and similarly then 1 star proving that bool star holds of 1 and 1. So now, of course, I have introduced a new binary relation into type theory, which wasn't there before. But fortunately, the pattern of these introduction rules, which define it, follows the general pattern that is formalized in Koch, for instance, or general pattern for inductive definitions, which means that it's automatic once you have seen these the formation and the introduction rules to generate the elimination and equality rules. And that pattern gives us, in this case, these are now the elimination and equality rules for bool star, this new constant bool star that I introduced. And that does not give us directly the interpretation of the elimination and equality rules for a bool, but they can be constructed from these. So we have to write up the straight elimination and equality rules for bool star first, elimination and equality. So now it's unfortunately under there, but it's clear we will have to consider a family of sets with 3 arguments now, D, Z, Z prime, and R, let's say, where this is a set with Z and Z prime in bool, and R being an arbitrary proof of bool star of Z and Z prime. And then we need to have a proof D0 that 0 star, 0 and 0 star together satisfy this propositional function or family of sets capital D, and similarly D1, proving that D of 1, 1 star. And then the elimination rule says that we may introduce a function f of ZZ prime R, say, with values in DZZ prime R with the same as there. By the following scheme, then we apply f to the canonical forms of R, which are given by the introduction rules. So which have their types that we see up there. So these are the bool star elimination and equality rules. Now we have to see to it that by means of these rules we can interpret the what the usual rules of bool elimination and equality come out as in the model. So now I think we have to write up the bool elimination standard Boole elimination and equality rule. So there we have a family of sets C of Z over Boole, and we have a proof little c0 of that C is true of 0, and the proof C of 1 that C is true of 1. And we conclude the rule allows us to introduce a function f of z in C of z for z in Boole by putting f of naught equal to C of naught and f of 1 equals C of 1 and C of 1. So that's the standard rules. And how do they come out in the model? Well, we have to put a star on everything. And if C is a family of sets over Boole, then in the model we will have a family of sets, or rather relation if you want, C star of Z, Z prime R, say, which is a relation between C of Z and C of Z prime. For Z and Z prime in Boole and R in Boole star of Z and Z prime. That's the first premise. Second premise says that we will have a C0 star in C of 0 star. But what is that? That's something I have forgotten to say, but it doesn't matter really. You see it from this particular case, what the pattern is. How the star operates when you have a substitution. It will be C star of 0, 0, 0 star. And similarly then C1 star. Sorry, of. It's a so far it's only a relation. So we have to put in C of 0, C of 0. And C of 1 star is in C of 1 star, which is equal to C star of 1. These arguments should have been here, of course, also. Yeah. And then, so that's what is given, because we have already managed up to the line. And now we have to provide the right things below the line. So we have to define f star of the three arguments z, z prime r, which should be in, we let the star work on this, we get C star of z, z prime r on f of z and f of z prime. In the obvious context here. And moreover, we have to see to it that the interpretations of these equations come out correctly. That is, we have to convince ourselves that the f star that we still have to define is such that f star of 0, 0, 0 star is equal to C0 star in its type, and similarly f star of 1, 1, 1 star is equal to C1. And the types of C0 star and C1 star are here. So how do we define that f star? Well, we have to make a particular choice of the family capital D in the Boole star elimination rule. And what is that choice? It should, we simply take it to be our C star, which we have already of Z prime R, applied to the f that we have by assumption in the standard elimination rule, f of z and f of z prime. I won't write out the context. So let that be our family D. What do we get then? Well, we also have to have those two premises, of course. So I have to choose D0 to be the right thing. And D0 should clearly be taken to be C0 star, which is in, and here I think I will make the calculation in one place. So that's the type of C0 star as we have it here. But now remember that we have defined f of 0 to be C0. So this is definitionally equal to C0, C star of 0, 0, 0 star of f of 0, f of 0. And that is nothing but the capital D that I have chosen here, evaluated for 0, 0, 0 star. So that means that I have now got this premise, and of course for 1 it's similar. And that means that I can apply this rule and get an f now, which satisfies what? Let's see. Yeah, it satisfies directly what it should, I think. So I get an f satisfying this, and that f is my f star. So I take f star of z prime r to be simply the f that I get as a conclusion in this rule. and then the verification that it satisfies these equalities is clear, because I simply define this to be f z z r. And with that definition, we now have to see to it that f star of 0, 0 prime, 0 star, 0, 0, 0 star, that becomes f of 0, 0, 0 star, which is equal to d0. But d0 I chose to be c0 star. So I'm now done with the Boole rules. And this is the pattern. This is the pattern followed for all other rules, including pi and the universes. I think I should at least begin. I'm not getting through it, that's clear, but you can so that you see the complexity of the pi rule. It's the interpretation of the pi rules that gives us function extensionality. Indeed, the introduction rule for the pi introduction rule in the model is essentially the extensionality principle for functions. But let's look at it now. We have to interpret pi a b in the model, so we have to define what this is. And because of the way the interpretation star operates, this should be pi star of a star and b star. It's the pattern that we have seen several places already, where this is a new operation that I have defined, that I have to define. That means that I have to introduce a new function type, pi star, which has 6 arguments. Sorry, it's not a function type. It's a it is a function because it's a relation between 2 sets, and I will show what the 6 arguments of a pi star are. So we now have pi star formation. So suppose that we have a set A and another set A prime and a relation P between A and A prime. And we have a family of sets B of X over A and another family B prime of X prime over A prime. And now that we also have a relation Q, now heterogeneous, which relates B of X to B of X prime. So we have Q is a relation X prime P, which is a relation between B of X and B of X prime, B prime of X prime, for X in A, X prime in A prime, and P in capital P of X and X prime. Under these premises, we can provide pi star with its arguments. It's 6 arguments, which are precisely AA prime P, and B prime Q. And what does it give us? Well, it gives us a relation between pi of AB and pi of A prime B prime. So pi star has to be defined in this way in general, and then we can use it on the diagonal to get the interpretation of pi of AB. This is a new relation with 6 arguments and 2 more arguments here. So it's a propositional function with 8 arguments, in fact. And how do I define such a gadget? Well, it's after all a propositional or set-valued function, so always by the introduction rules. So there is a rule of pi introduction, which, as I have already intimated, essentially states the extensionality. And there is a corresponding elimination and equality rules. And using them, I can validate the interpretation of the standard pi rules in the model in exactly the same way as I validated the interpretation of the Boole rules in the model. And this works also for universes, where the most difficult case to check that I have checked is to handle that the universe is closed under pi in this model. The star for the universe, yeah. So, so we will have a U star formation, which, that's clear. It's like in the Boole case. I mean, it has to be sorry, it has to be, U star has to be a relation on U. And then the elimination rule for U star is the decoding function, and I'm using Tarski style here. So I will have A in U, A prime in U, and I have the proof P that of U star of A and A prime. And this will give us T star of AA prime P, which is a relation between T of A and T of A prime. And this U star is, of course, defined by its introduction rules. Has to be defined by its introduction rules, which are just what taking the usual U introduction rule in the model instead. That will give you the U star introduction rules. And T star, on the other hand, is defined, so you have to show how it operates on a P here, which is of canonical form.
So there would be one U star introduction rule for each
Yep.
element of the
Yep.
universe.
Right. Which means that we double, we still have our old ones. Yeah. All this, which involves star, is added to standard types here to get this non-standard extension. Yeah, so enough about the universe, it's natural to call this universe the extensional universe as opposed to the original U and T. U and T is the intentional one, and U star T star will be the extensional universe. So I would like to stop now in order to have some comments, but yeah. No, U is closed. So U is interpreted as a relation. U star will be a relation on U. So that's correct. Now I just want to mention a possibility that becomes available. Since I have started from this principle that isomorphic structures or isomorphic objects are the same, which is the intuitive starting point for Vladimir in his univalence axiom. The question is how it comes out in this framework. It's clearly not his univalence axiom, but it becomes possible to formulate an invariance axiom stating that everything is invariant. And what is it I have established? I've established that all definable objects of type theory are invariant. But to say that everything is invariant, I mean, it's just not the case. If you take seriously the meaning explanations for type theory that everything is invariant, you have to prove by a lot of work, as you see, by induction over the syntax that every definable thing is invariant. But now, if we have a context A1, if we have sets A1 up to AN of x1 up to xn minus 1, as usual, then A1 is closed, which means that A1 star is just a relation on A1. And something is invariant if it is related to itself. That's the definition of invariance. So if I want to say that an arbitrary element of A1 star, of A1, x1 say, is invariant, I can do that by introducing a new function symbol here, which says that x1 is related to itself. And you see that appears as the reflexivity proof for A1, which A1 was an arbitrary relation, so it wasn't reflexive before necessarily. And similarly then up to 1 of xn here and here remember that an has 3 times n minus 1 argument, so you will have x1, x1, 1 of x1, so they have to come in order in this way up to xn minus 1, xn minus 1, 1 of xn minus 1. So these are the new axioms, the invariance axioms. And by means of these invariance axioms for elements, you can prove immediately that every set also comes out invariant, because if you put in capital A star, where A star depends on variables of these types, we can do the same thing as we did here. So we get A star of x1 x1, 1 of x1, etc., xn, xn, 1 of xn. This is now a relation between a of x1 up to xn, and no longer a of x1 prime, etc. Now we have x1 itself here, so it's a self-relation. And this relation functions as the proof that capital A is invariant. So these are the invariance axioms. And now the question is, what about these axioms? Can they give rise to contradiction, for instance? Are they valid? So it seems to me that the answer is the following. They are not valid as they stand, thinking of the variables here as ranging over x1, etc. So in this case, it will be x1 in A1, because we, from the explanation of what it means to be something, an element of A1, it doesn't follow that it necessarily is invariant. So it's not valid in that way, I mean, interpreting the variable x1 there in the standard fashion. But on the other hand, if we choose instead the model of definable objects in type theory, the syntactic model, if you want, then, of course, it is valid, because then what x1 ranges over are the definable elements of A1. And if we take a definable element, A1, in A1, then its interpretation, since it is defined, it has an interpretation, and that interpretation belongs to A1 star of A1 and A1. So that means that we have actually an interpretation of this, namely in the model of definable objects of type theory. And that should be considered, I think, as the natural analog of the model of constructible sets for set theory. It should be the model of constructible objects in type theory. And what is a constructible object in type theory? Well, it's one that can be constructed by means of the constants that you have in a particular fragment of type theory, if you think of type theory as open. So this much about the invariance axiom, and then I just comment at the end here. Probably several of you listened to the talk that was given in the end of October by Nima Arkani Ahmed about the inevitability of the physical laws. He, at one point in the talk, speaking about the physical laws, he wrote up 3 characterizations of them. One was what he had in the title, inevitability, and the second was the dual character of both rigidity and fragility and beauty. Now, I have nothing to say about inevitability. I don't know how wise it would be to say anything about that here. But if I can delete that and perhaps put simplicity here instead. You see, it should be clear from this kind of work. I mean, this is a model construction. And you have to be extremely systematic in this. I mean, it's the it's as with the original formulation of type theory. It's a certain conceptual pattern that you see. And this conceptual pattern is, in a sense, very, very rigid. I mean, so rigid that many people thought that no one is ever going to subject himself to that kind of rigor in his mathematics. So it's very rigid, but at the same time, it's extremely fragile. I mean, if one begins to tinker with this a little bit in some corner of this whole system, you never know what happens. And as some of you know, I mean, I have made mistakes at certain points. And in one case, didn't become inconsistent, but the result was quite disastrous in other respects. And so this combined character of rigidity and fragility, fragility seems to me to apply equally well to systems of logical laws, logical set theoretical laws as these ones. And it's similar with the last two characterizations, with the beauty and simplicity. I mean, this is, of course, a complex system. You see, I have checked a few of the most crucial rules, and in explaining this to you, I have had to leave out almost all of them, and have succeeded with the Boole rules and a little more. But it's because of the rigidity and systematicity of this pattern that one can handle structures of this kind. And especially since I am forced to handle it by hand in my usual way, now things are better. I mean, Thierry is checking the setoid model on the computer, so he is in a much better position, but I'm still doing it by hand. Thank you.
Very similar to an instance of the more general inverse diagrams picture that I sketched at the end yesterday, where maybe the diagram shape is a span shape.
Yeah, exactly.
Yeah.
One can see it. This is very closely to the logical relations model.
Right.
Basically the same as the logical relations model, and the logical relation you can see as a span. So it's the.
I was thinking that all the way through, and then I got confused with what you said about the universe, because the logical relations thing, it seems to me like what you would do is you would say that U star of A prime would be like the set of all relations between A and A prime.
No, that's not U star, that's set star. If I use but sorry, there should be much more here, of course. No, so set is closed. So set star should be a relation between two sets. Yeah. No, it's the function type set into set, isn't it? Good in that case. So what is set star? It should take set star should take two sets, A and A prime, into a type in my terminology. Isn't that right? Yeah. So I define set star equal to set in type. Yeah, but then if we abstract it, I'm so tired that it's possible that I'm getting things wrong now. But set star then will go from take a something in A and A prime into set. This is the type of relations between A and A prime.
Actually, set start out being a prime.
Ah, but there we have it. Good.
So why do you want U to be different from set?
Well, that's what I asked.
Oh,
Why would you want U star of A and A prime to be different
oh.
from
So
set
now,
of A prime?
yeah, now we have really a problem of standard type theory that has to be settled. I mean, we have, and it's similar in the ZF foundations of category theory. I mean, we have sets which belong to a universe, and these universes are themselves sets. So to belong to a universe and to be a set is not the same thing. So that means that we have what I would call perhaps small sets, which is the same as set in a universe. And then we have set, and then we have type over that in my terminology. Or if you want type here, you will have type here.
Shouldn't you start with something like A prime to A universe?
Yeah, that's what I was thinking.
Well, yeah.
So U is a set, that is clear. And I have said quite generally that any constant or closed set is interpreted as a relation over itself. So U star should be a relation between U and U.